This is take 3. So this is number 24 on test 1. Question reads, a catalyst decreases the activation energy for a reaction by 15 kilojoules per mole. How much faster is a reaction at 25 degrees Celsius with the catalyst than without? So two things, well, basically about catalysts, okay? You're basically making this reaction faster because you're decreasing the activation energy. This is take 3, so I really don't want to draw this graph. So I'll just keep going. So I'm going to use arrhenius. If you see activation energy, something should click. And you should just say, oh, look, I'm using the arrhenius equation, okay? So the arrhenius equation, as we're going to see it on the data sheet, is K is equal to A times E to the negative activation energy over the gas constant times the temperature in Kelvin, okay? I don't like seeing it this way. I like instead multiplying it by K on both sides. The reason why is because that allows me to bring negative EA over RT down, okay? It's no longer a power of E. For example, if I do ln of E to the, let's say I do ln of E to the, E squared, okay? What this will turn into is that the ln will cancel, the E will cancel, and the 2 will be brought down, so I'll end up with 2. Likewise over here, if I do ln of E to the negative EA over RT, I'm going to end up with just negative EA over RT. We bring that down and we take away our natural log and we take away E. The other thing I need to bring here is one of the logarithmic rules. So we say that if we have ln of A times B, it's also equivalent to ln of A plus ln of B. Okay, now we're not saying here ln of A times ln of B, we're saying of ln of A times B. That's a very, very important distinction. Okay, so it's the same thing here. I did basically ln of capital A E, to the, or A times E to the negative EA over RT. So this originally would have been ln of E raised to the negative activation energy over RT plus ln of A. But because I said before that the ln cancels the E and brings down the exponent, we don't need to worry about that so much. But that's why we have an addition here. It's simply an extension of one of our logarithmic rules. So what I'm going to do is I'm going to use K2. I have a reason for that. I will explain that soon. I'm checking to make sure that this thing isn't sideways because before I was recording this upside down and sideways, and that's why this is take 3. But anyway, I know that my initial condition, and don't worry about this too, just remember that this is K initial. My initial condition has a higher activation energy. Basically when I add my catalyst to it now, the activation energy goes down, and I want to find out how much greater the rate is than 1. Now, K is not the same thing as rate, but right now we're going to assume that they are basically the same thing. Okay, if I went into the derivative rate law, you could see why, but we're just going to assume because that's a magical tool for economists. Anyway, so we basically will plug these into our original arrhenius, or rather the James expanded arrhenius is how we'll call it. Because I am important like that, and I've been studying too much bio, where we have things like nodes of Ranvier. Anyway, so we've got ln of K2, we've got ln of K1. Likewise, I know that I have different activation energies for both. So I have EA2, and don't be confused here. I'll try to cross this stuff out. That's a mistake. This is actually negative EA, subscript 1 over RT1. Okay, I'm just trying to differentiate that I have different conditions for both of these potentially. But I have to mention here, I have a constant temperature. No matter what, the reaction is at 25 degrees Celsius, which is 298.15 Kelvin. Okay, the other constant I have here is the change in activation energy. So I'll go into that now. So in order to find that out, okay, in the past when we've been asked for what the hell is activation energy, we assumed that activation energy was same whether we were using K1 or K2, okay? So in order to basically create a relationship between these two equations and to eventually extract out, let's say, how much K1 is in relation to K2, keep in mind that K1 is with catalyst, K2 is without. You can choose either one. I just choose to use K2 for a very good reason, which we'll see soon. All right. What I'll do is I'll subtract. Okay. So I'll say ln of K1, whatever, and I'll subtract ln of K2. I'll end up with ln of K1 over K2 is equal to negative, first activation energy over our first temperature plus the second activation energy over the, RT subscript 2. Okay. Now, another thing I need to mention here, or reiterate rather, is that I have the same temperature for both cases, and chances are I've got the same R. Okay, so what I'll do is over here, I'm assuming I can rotate. Okay, let me try to explain this in logical terms. Basically, if I were to take negative EA1 over RT1 plus EA2 over RT2, it's the same thing as me doing EA2 over RT2 minus EA1 over RT1. It's just me flipping, okay? So I'm going to do that. And I said that my EA2 over here, I have a higher activation energy than my EA1, right, which has lower. So if I were to do EA2 minus EA1 and set that over RT, because RT, you know, to be honest with you, both of those are the same for both of them, so I'm just going to create one little denominator right over there. Well, in that case, if this is big, that's small, isn't that the same as saying the change in activation energy over the the gas constant times the temperature in Kelvin? It is. And what I'll do is I'll plug in, because over here it says the activation energy for a reaction has been decreased by 15 kilojoules per mole, okay? So, and if you were to basically do it the other way, you can make this negative EA, you know, whatever. You could basically make this negative change in EA. But because I did EA2 minus EA1, I did big, you know, small from the big, I can end up with just a positive number over here. So I'm going to do that. So here's the exact same thing written a lot bigger, just in case you couldn't read it before. And what I'm going to end up with, and this is why I did K2 is equal to 1. It's because I have K1 over K2. K2 is equal to 1. So I have ln of x over 1 is equal to, and keep in mind over here, I have to convert my kilojoules to joules, because my gas constant here is joules over kmol, not kilojoules over kmol. So I have ln of x over 1 is equal to 15,000 joules over 8.314 joules over kmol times 298.15 Kelvin. This x over here is my K1. I made K2 1, so that way I could simply make this ln of K1, which is the same. It's the exact same thing. So here we go. I basically can work out the right side. I get 6.051, however many units. I was too lazy to write it down. I believe this is moles. No, I'm not even going to bother. Don't worry about it. I've got ln of x is equal to 6.051. I'm not done yet. Remember how before I said that I can do the ln of e to the whatever power, so I can do ln of e squared turns into 2. Well, if I do e to the ln of x, I can bring the x and keep it alone. So I'm going to raise both sides to powers of e. So here we go. E to the ln of x is equal to x. E to the 6.051 is equal to 424.5. So I know that x, which is the same as my K1, is 424.5, or 426. Considering the fact that my K1 is 426, and my initial K2 is, well, it was 1, wouldn't you say that 426 is 426 times my initial condition? So as a result, this is 426 times faster.